Okay, so for number 15, we're trying to complete the proof of theorem 2.2.3. And since we're trying to show for all these that they're equal, what we're going to do is we're going to choose a if and only if chain of reasoning. So for item A, we're going to begin with this side, but we're going to do if and only if, and then show that it leads to that. However, because it's if and only if, we can, once we're finished with it, we can also retrace back our steps by beginning from here and then showing that it does lead back to that. So we're going to say we have that x comma y belongs to A cross B intersection with A cross C, because as we're doing an intersection of cross products, the element that is in it must be a coordinate point. So we're going to say if and only if xy belongs to A cross B, maybe I'm going to remove this, and xy belongs to A cross C, right? And then from there, we're going to say if and only if xy belongs to A cross B, it means that x belongs to A and y belongs to B, right? And if xy belongs to A cross C, it means that x belongs to A and y belongs to C. So now, because we're trying to show that it's the same thing as A cross B and C, so what we're going to do here is we are going to just rearrange this, right? We're going to rearrange this and say if and only if x belongs to A, right? Because these are all a bunch of and statements. So we're going to say x belongs to A and y belongs to B and y belongs to C. Because the thing is, since I repeated this x belongs to A and x belongs to A twice, I can just go ahead and eliminate one of them, and logically speaking, it won't make a difference. So let me erase this. That should be x belongs to A, and y belongs to B, and y belongs to C. And maybe I'm going to put a parenthesis here, and now we can just say if and only if x belongs to A, and if y belongs to B and y belongs to C, it means that and y belongs to B intersection C, right? And so from here we can say if and only if x belongs to A and y belongs to the intersection of B and C, it means that x comma y belongs to A cross B intersection C. So that's it for item A, where we began assuming this and we showed that it leads to that. However, we can also go backwards, right? We could have began the proof here and then gone, okay, if xy belongs to A cross B and C, it means this, and then it means that, and so on, and we would eventually arrive here. So because we used if and only if, we can go back forwards and backwards, and so we have shown that they are equal, right? So our conclusion is going to be, thus, A cross, B and C is going to be equal to, that should be, let's see, A cross B intersection with A cross C. And that is it for item A. Now let's do item B, and we're going to do this one by contradiction, right? So we're going to do this by contradiction. We're going to say for B, we're going to say suppose that xy belongs to A cross the empty set. And so then what this means is that x belongs to A and y belongs to the empty set. But y cannot belong to the empty set, as the empty set has no elements, which is a contradiction. So because it is a contradiction, so what does that mean? Thus, the conclusion is xy does not belong to A cross the empty set. Now, we haven't assumed anything about x and y. We just said they're just, it's just a coordinate point, right? And so since there are no coordinate points in A cross the empty set, this implies that, I'm going to say this implies that there are no elements in A cross the empty set, so it must be the empty set. Therefore, A cross empty set is the empty set. That's it for item B. So whenever we're trying to deal with the empty set, usually it is a good idea to do it by contradiction, right? That's it for item B. Now let's do item C. And item C is going to proceed similarly to item A, where we're going to do if and only if chain of reasoning. So we're going to begin. Let's see where we're going to begin. So for item C, we're going to say we have that xy belongs to A cross B intersection with C cross D. So we began by showing that some element here, and now we're going to show that by if and only if chain of reasoning, it must be over here and vice versa, right? And so if xy belongs to A cross B intersection C cross D, if and only if x comma y belongs to A cross B and x comma y belongs to C cross D. Now let's unwrap this even further. So if and only if xy belongs to A cross B, it means that x belongs to A and y belongs to B. That's the first one. And if xy belongs to C cross D, it means that x belongs to C and let me do this in lowercase. If and only if x belongs to C and y belongs to D. Okay, so all we've done so far is we basically unwrapped the meaning of this, right? So now that we have completely unwrapped it and we've shown that, okay, x is in A and y is in B and x is in C and y is in D, what we're going to do here is just kind of rearrange this, right? So we are going to say, if and only if, we're just going to rearrange this. So we're going to say x belongs to A. Let me improve this. X belongs to A and x belongs to C. So what we've done here is we've taken these two and just kind of put them together, which we can do because these are all and statements, so the order here doesn't matter. And now we're going to rearrange the y's, right? And we're going to say y belongs to B and y belongs to D. So now that we have rearranged these, we can now apply the intersection. If and only if x belongs to, well, if x belongs to A and x belongs to C, by definition, x belongs to A intersection C, and y belongs to B and D, so y belongs to B intersection D. And then from here, we can say if and only if x belongs to A intersection C and y belongs to B intersection D, x comma y belongs to A intersection C cross B intersection D. So that's it for item C. So we began here, but that was arbitrary. We could have also began here and shown that, hey, from here you can go reason through there, and then through here, 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 and so on, and eventually arrive at the conclusion the opposite way. So this works both ways. So we have proved the equality, which is a double inclusion. So for item D, we're going to have a very similar chain of reasoning, and we're going to say, we have x, y belonging to A cross B intersection with B cross A, and like we did before, we're just going to unwrap this bit by bit. So first, let's unwrap the intersection. If and only if, we're going to have that x, y belongs to A cross B, and x, y belongs to B cross A. And now we're going to unwrap the cross product. So if and only if, we're going to have x belongs to A and y belongs to B. So that's the first cross product, right? And we're going to say x belongs to B and y belongs to A. So that's the second cross product. So we have unwrapped the statement entirely. And now let's think about what we want. So what we want is to show that A intersection, we want to have it A intersection B cross A intersection B. So to get an intersection, we're going to just rearrange this. We're going to say if and only if. I want x to belong to A intersection B because that's where the first element is going to go. So I'm just going to rearrange the and statements. I'm going to say if and only if x belongs to A. So that stays where it is. And now I'm going to bring this guy here right in front. So I'm going to say if and only if x belongs to A and x belongs to B and y belongs to A and y belongs to B. So all I've done here is I've rearranged these and statements, which I can because with the and it doesn't matter the order. And so once I'm here, this implies that if and only if x belongs to A and x belongs to B means that x belongs to A intersection B, and similarly y belongs to A intersection B. And y belongs to A intersection B. So if x belongs to A intersection B and y belongs to that as well, it means that x, y belongs to A intersection B cross A intersection B. And that is it for item D.